Shall we continue? All right. So let's continue our workshop, our tutorial. So now in pass 3, we're going to get slightly more technical. So some time ago, I searched this on Google search. Who is Margaret Atwood? And Google search gave me these 3 pieces of results. In item 1, you can see that I got a list of websites which were relevant to my search query. In item 2, you can see that I got some sort of a summary about Margaret Atwood. And in part 3, you can see that actually when I use the desktop computer, you can see that some parts of the return text from each of these websites was shown with a bold-face font, right? So my question for you is, between number 1, 2, and 3, which ones do you think were had BERT in them? So BERT was a product of Google, and Google search engine is also something they care about. So it's natural to think that they used BERT for improving Google search. My question is whether they use BERT for number 1 or for number 2 or for number 3 or for 1 and 2. They could have used it for multiple of these applications that you see. So raise your hand if you think BERT was used for ranking these relevant search results. So this is a search query about Margaret Atwood, and in item 1 I got a rank list of websites. So my first question is, do you think BERT was used for ranking these websites? Raise your hand if you think the answer is yes. All right. And now, if you think BERT was used for getting this this overview, this summary that we have in number 2. Okay. Also in the chat, feel free to type, answer the questions. Okay, I can see hands raised among the online participants. All right. And what about item 3? What about those highlighted texts? All right, perfect. All of you answered correctly, because BERT was used in all 3 of these. So we have been using BERT, not just us, even like my grandma has been using BERT for 6 years, just she doesn't know it. So for text encoding, this is one use case of BERT. So instead of just looking for exact keyword matches, Google search actually does text encoding, and that is why we would get relevant result even if there's a misspelling in how we type Margaret Atwood. We would still get relevant result because the misspelled version of Margaret Atwood has a vector that is very close to the correctly spelled version. So this is maybe one advantage that Google search had 7 years ago, and maybe some of its minor competitors didn't have back then. Or probably text encoding is from some earlier time. Also, similarity retrieval. So another feature of Google search is that it returns relevant websites, and the way that similarity between different websites and the search query is measured is based on measuring the similarity between the 2 vectors. So that's another part where BERT is essentially involved with Google search. We have extractive text summarization, as you can see. So this sentence that is shown in item number 2, actually we don't have that in Wikipedia. If you check Wikipedia, there will be a longer paragraph that is certainly longer than these 3 words, but BERT is used by Google search to summarize, to extract a summary of that paragraph that is relevant to my search query. So maybe in the original Wikipedia paragraph, there's also the birthday, and there's, I don't know, look, the, you know, where she was born and these sort of things, as it is typically the case on Wikipedia. But as you can see, those parts were removed, right? And item 3 is essentially question answering. This is my search query was who is Margaret Atwood, which is a question, and BERT was used to highlight a part of each of these kind of catch text that could be a relevant answer to my question. So a relevant answer to who is Margaret Atwood is a founder of Griffin Poetry Prize and the winner and the Writers' Trust of Canada. Another potential answer to my question is a varied and prolific writer, right? Another potential answer is a poet, novelist, writer, essayist, and environmental activist. And for those of you who are visiting from other cities and other countries, yes, Margaret Atwood is from Toronto, so I'm very happy to be in a city where she is from. All right, here is another use case. For those of you who have used Gmail on your phone, you might have tried, you know, some of these smart replies, where specifically when you get like a short email, it gives you like these options to choose from, and this is, you know, another rather low risk, you know, low risk usage of these systems, because they are not, you know, that reliable. But if the user is given the option to choose from what is provided to them, you know, the user has the responsibility, so they will choose only if, you know, they are useful. And, you know, every now and then we might have received, you know, these smart reply options, and none of them were relevant, right? That, of course, that shows, you know, the limitations of BERT. Any questions so far? All right, so that was pass 3. We are halfway through learning all details of the BERT language model. Now we're getting a bit more technical. So, when I showed you the timeline of developments in this field, you may remember that we had attention mechanism, transformers, and BERT. They were, you know, major breakthroughs in 2010s. So attention mechanism was fundamental for the architecture and for the architecture that came to known as transformers, and the transformer architecture was fundamental in the development of BERT. So let's see what attention mechanism does. So what you see on this slide is a search query about parking on a hill with no curb. Before BERT was introduced and was integrated in Google search, and after BERT was used in Google search, the results are quite different. Before BERT, you can see that when someone searches for parking on a hill with no curb, they will get this. They will get instruction about parking on a hill. And in the instruction, you can see that it's about parking on a hill with a curb. Why is that? Because before BERT, this search query used to be processed based on its keywords. So the main words we had were parking, hill, curb, right? So Google search before 2016 was doing, you know, the best it could possibly do. It was like giving us result about parking, hill, and curb. The poor thing just didn't know that no is so fundamental to processing this query correctly. And for those of you who have been in a situation of using Google search to learn how to park your car, if it was before 2016, that could have resulted in a major, you know, accident, right? But after BERT, now Google search knows that the word no is fundamental in processing this search query correctly, and it has to return results which are about parking on a hill with no curb specifically. So in here, this is what we call, attention mechanism. So this is called attention mechanism because the way that this sentence is embedded is that when the encoder, when BERT model is processing the word curb, there's some information from other words in that sentence which can affect the way that the word curb is converted into a vector. And through its training, it learns that when the word curb is there, and when the word no is in the sentence, it must be given a lot of, it must receive a lot of attention, it must have a lot of influence on how the word curb is embedded. Because curb and no curb are fundamentally different to the point that the embedding of the word curb after no must be different, should be different from embedding of the word curb that is after anything other than no. So this is the attention mechanism. Questions? Yes. Sorry? Yes. Sorry, where? Oh.
How easy is it to translate this mechanism for other languages to have a different structure of words?
Well, there are different versions of BERT for different languages, and there are also some versions of BERT that can handle different languages. So I don't know how difficult it was for the teams who developed those models, but we know that they exist. So, and they are accessible to us. So for us using them, it's as easy as loading something from Hugging Face or from TensorFlow Hub.
How good is it when it comes down to when the phrase consists of like sarcasm or different like ironies?
Yeah, BERT was not specifically designed for being able to support sarcasm, but I mean, it solved many challenges of that time, which were about incorporating the context into account. So I would say if sarcasm is important for the application you have in mind, probably BERT would not be the best model, but there are definitely models where the capability of supporting and kind of understanding sarcasm is built into them, to the point that you will see the word sarcasm in the description of that model. So if you maybe search on Hugging Face or TensorFlow Hub for sarcasm, you will find models where the description says this also handles sarcasm. Yeah. But you can imagine that at the bigger picture level, this is about context, right? So we understand sarcasm because we understand the context, right? All right. So so language is considered as one of the most fascinating inventions of humankind, and one reason for it is because it is both limited and limitless. So in the wise word of contemporary poet and philosopher, words in finite chains, yet boundless realms they unveil. And this is, of course, from my favorite philosopher, ChatGPT. So Google receives 8.5 billion search queries every single day. I have another question for you. Out of these 8.5 billion search queries, how many of them, what fraction of them do you think are new search queries, are things that Google search has not seen before? So again, any number between 0% and 100% is a feasible solution to my question. So the question was, from the search queries that Google receives on a given day, what fraction of them are totally new? There's a number. We just want to get the idea of whether we're talking about 1% or 1/1,000%. Because if it is very small, then because Google has existed for such a long time, search is solved because it knows based on how users interact, it knows whether it did this search query right or wrong, and it can adapt. Yeah, but this is not a philosophical question. This is just a guesstimation question. So this is just a guessing game, and I care about the order of magnitude of your question, of your answer. Yeah? Less than 1%? Yeah. 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 But let's think about averages. So just think about a typical day, some average day. All right. What is that percentage considering everything? Because many of you know a lot about stock market, and they say everything will eventually represent itself in the price. So let's say everything, even the hockey game and baseball games and I don't know weather and war and inflation, everything eventually represent itself in a certain usage of Google search. Think about that average usage and what fraction do you think is totally new?
On a given day compared to a prior day?
No, compared to all history of Google. Yeah.
Still, 15%.
15%. Anyone else? Yeah? 5%. 1%. 2%. Many of you guess relatively small numbers. Anyone else wants to make a guess? All right. It is actually 15%. Very, very on the spot. So what this means is that, despite how big Google is and how commonly its, search engine is used, search is not a solved problem. So this is another quote, hopefully this time not from an AI chatbot, but VP of search at Google, who said at some point that BERT has been one of the biggest leaps forward in the history of search. So despite how simple and accessible BERT is, it was a big deal in 2017. And based on the fact that we all have been impacted by it, including my grandma, who uses Google search, it is still, I think, a big deal. All right. Now let's move on to past 5 and get a bit more technical. Any questions so far? Please do.
This number I think is very interesting because it somehow could be interpreted as a measure of how well they are doing, right?
Yeah.
Because usually whatever you search is reflected in the result, right? And the result is basically the reference, right? And you can just estimate that from different angles. For example, mathematics, it is known that every 5 years, for example, the size of the mathematics doubles, right?
Yeah.
So basically, and the reason that I told 2% was just to divide
Yeah.
to doubleness.
Yeah. But for Google, I think it was easy. They could also, I can see in the chat that people made some good guesses. Pretty much, it's normal to guess something very small for this because, and that's because language is limited. We have finite words, but by combining them, because of the combinatorial explosion, we can always come up with new sentences or new things to ask Google. And apparently, people have been so innovative over the years that every day Google still receives 15% new queries. Yes, but yeah, it's, I guess for Google, it's easy to measure that. All right, so transformer is just a fancy word, but it's as simple as addition of two other fancy words, encoder and decoder. So a transformer architecture is made up of two things, encoder and decoder. And I guess for many people who want to learn about BERT or the transformer architecture, they see this plot, which is, I guess, an excellent plot for a scientific article, but for, I mean, also it's excellent for another purpose, for dissuading people from, from learning about transformer. Because you see this, there are like different colors, like different, jargon, and things are connected to each other in a certain way, and they go up and there loops back and so on. So at least for me, when I saw this figure for the first time, I think I just closed the PDF file of the article and I went on and did my, graph theory stuff that I prefer over this. But if you're seeing this for the first time, you're in luck today because I'm here and I can guide you through understanding what is going on. So first of all, it is made up of two parts. The left part is the encoder, and the right part is the decoder. And again, we are in luck today because BERT is an encoder-only architecture, so we can easily get rid of this. It just gets better and better, right? So we just need to understand this part. This is essentially the architecture of BERT. So E stands for encoder. All right, so in this encoder, as you can see, the input comes in. There's positional encoding, we're going to talk about it. And we have different layers where vectors are like multiplied to something and added together and then sent to the next layer to multiply to something. So each layer is just a multiplication, addition, and those sort of arithmetics. And what the developers of BERT did was that they put 8 of these so-called encoder layers on top of each other. And so we can think of BERT as a stack of encoders. So our current working definition for what BERT is that it is a stack of encoders. We saw what encoder is. When we put 8 of them on top of each other, you can call it BERT. And later, we're going to make this definition a bit more precise. All right, so we talked about these three. Let's learn more about them. Attention mechanism, transformers, and BERT. So this was sort of a simplification of what was going on because just actually in transformers, we didn't have just attention mechanism, but we also had positional encoding that we saw on the previous slide. And for attention, we actually had a very specific flavor of attention mechanism called self-attention. So let's talk about this to understand what a transformer architecture does, and then that helps us understand why BERT works. All right. Think about this sentence, Alice dumped Bob. So Alice and Bob are just two names I've used to hide the identity of two of my friends. And if you talk to Alice, she's very specific about the order of words in this sentence. That it was Alice who dumped Bob, not the other way around, right? So you can see that the order of the words matter. I mean, specifically to Alice, it matters so much. Like she gets so mad at you if you say it the other way around, right? So now we need to consider that when we are embedding these words, the position of the words must also be incorporated. How can we do that? Easy. We just slap a label to each of words. So instead of embedding Alice, we're going to embed Alice in position 1 of the sentence. Instead of embedding the word dump, we're going to embed dumped in position 2 of the sentence, right? So instead of dealing with words, we deal with words that have positions incorporated into them. Bob will be Bob in position 3, right? And by doing that, we can have positional encoding. That's it. Questions? So to me, it's very fascinating that the ideas behind BERT were so simple and intuitive, yet they led to a model that was so fundamental, and we are still using it in Gmail and in Google search and so on. And apparently, like back then in the dark ages of language modeling, people didn't do this. People would, or in RNNs, the embeddings, were just based on the words, or in n-grams in word2vec, we would just embed Bob, and then we had, we shouldn't be surprised that the model cannot tell apart the two sentences, Alice dump Bob and Bob dump Alice. All right, we talked about attention mechanism already. So this example was about attention mechanism and how the encoder must pay some attention to the word now, to the word no, when it is encoding the word curb. But what about self-attention? So this is an example for self-attention. The pizza came out of the oven and it tasted good. So for the encoder to understand what it refers to, the encoder must see many examples of English sentences about oven and pizza and tasting good, to the point that it finds the associations between taste and pizza. So when we say like these language models understand, it's just about statistics. It's just about associations. These language models, when they are trained on large amounts of data, they see the association that there are so many sentences where pizza and tasted were together. So the co-occurrence of pizza and taste was a large number. But the same language model, when it is trained, it sees that there is no co-occurrence between oven and tasted. It doesn't make sense for oven to taste good, right? So when we say understand, it's all about statistics, and from that kind of co-occurrence statistics, the model would know when it is trying to figure out what this word refers to. The two options are oven and pizza. One of them makes sense statistically, the other doesn't make sense statistically based on previous things. So it has this kind of attention influence from each other word when it is encoding the word it. But because of what it has learned, it knows that when it is encoding this word in here, pizza must strongly influence the embedding of this word. So the word it will be embedded to a vector such that that vector is influenced heavily by the word pizza. That's how it can understand the context and the fact that it refers to pizza. And this is self-attention. Questions? Yes.
Question would be no attention at all to grammar, where like if you could have judged which one it referred to purely by grammatical constraints too.
Yeah. I mean, one of them is rule-based, the other is kind of frequency-based, right? So the thing is, if we want to like encode or incorporate grammatical rules, I think that would be more challenging. But with large amounts of data, this will be automatic. Yeah. Otherwise, you're right. And actually, we have attention heads. We have different attention heads in BERT model. This is a bit beyond the topic of today's lecture. And there are some attention heads that eventually handle grammar. There will be some that handle gender. There will be some that handle plurality. So, but we don't do that on a rule-based thing, but rather it is as if the neural network kind of organically end up with some capabilities used for grammar or mimicking grammar, something like that. It's very interesting when people start, trying to explain what each part of the architecture has done for a certain data set. We see that, oh, this attention head, it is capturing 40% gender and 20% plurality and 20% tense of the sentence. It's very remarkable and a bit scary. All right, past 6, so this will be the most technical. We have a question?
Yeah, just a quick one maybe to expand on this. Again, the inference here is based on statistical associations, but not necessarily tagging with parts of speech.
No, but you will learn more when I cover this pass, because I haven't explained how BERT was trained, and I haven't explained how it was fine-tuned. Yeah. So this is the part of the definition that now we're going to make it a bit more precise. BERT is a stack of encoders, but it's not just a magical stack of encoders that accidentally work. It has clever pre-training and fine-tuning. So before BERT, there were different other ideas of incorporating the sequential nature of the data in an RNN architecture, and they failed because RNNs were so expensive to train. But I think one reason why BERT worked was this. They had very smart pre-training and fine-tuning, and we're going to learn about that in pass number 6. Other questions? No questions. For those participating online, please feel free to just type your question in the chat, and I will answer you. All right. So for training, the training of BERT is called pre-training. This is because it comes in a there are essentially 2 steps that are used for preparing BERT for what it is supposed to do. The 2 steps are a training step and a fine-tuning. And as the training is prior to fine-tuning and prior to potentially more trainings later on, it is called pre-training. So it is a semi-supervised pre-training. What is the semi-supervised part? So semi-supervised is where we don't actively produce a labeled data set, but we define the objectives in such a way that the text, that the unlabeled text can be used for supervised training. So it's a smart way of kind of skipping the annotation part. So it had 2 objectives. Objective 1 was the so-called next sentence prediction. So with next sentence prediction, let's say the input was, my dog is cute, he is fluffy, right? And there are special characters. SEP stands for separator token, and CLS was the beginning of the input. So for objective 1, the question that the task is about predicting whether for a given pair of 2 sentences, whether the second sentence is indeed makes sense to be the sentence coming after the first one. So we have a pair of sentences, A and B. In some of them, they make sense to be one after the other. In some cases, they don't make sense. And in the pre-training of BERT, they use this as one of the objectives of training. So they essentially estimated the weights of the neural network so that it can correctly predict next sentence. And second objective was called mask language modeling, and I'm going to explain that later. So the only part, the only input that was used for objective 1 was actually this. The very first vector, this is the input. The input goes up, it goes to the first stack of encoders. First stack of BERT, and it becomes another vector. Then that vector goes to stack number 2. Then it becomes another vector. Then stack number 3. Stack number 3, 4, 5, this is stack number 8. And after stack number 8, we're going to just have vectors, right? The very first vector was used for next sentence prediction, meaning that that vector was then, let's say, given to a binary classifier, and it was trained based on 50% pairs of sentences which were indeed, which made sense one after the other, and 50% sentences which were randomly, patched together. One from Margaret Atwood's Wikipedia, one from something totally irrelevant, from some marine biology Wikipedia page. And then in the training, the weights initially are random, so the predictions don't make sense. And then based on the error, we measure the gradients, and then we do backpropagation to update the weights, and gradually the model learns. All right, so the pre-training input, we had pairs of sentences. These sentences had some special tokens. So this is a special token, CLS, we talked about it earlier. This is for classification or beginning of the input. We also had SEP, we talked about it. This is the separator token, right? So the input would be a pair of sentences. We have segment A or sentence A and sentence B. In half of them, they were actually consecutive. They made sense one after the other. The other half were just two random sentences patched together, right? And then, then these were used to train BERT. And this is semi-supervised because no one had to annotate the data. You could just use two sentences which were indeed consecutive in the original text and use them as consecutive sentences, consecutive pairs, and then you can pick any random sentence from one part, another random sentence, put them next to each other, and give it to BERT to see how it classifies them. All right, so this was the next sentence prediction task. Question? Any questions so far? Yes?
From the negative class in which we pay sentences that might not appear together, this is a guess. Maybe one day somebody would write those two sentences one after the other.
We needed large amounts of data. So with the semi-supervised idea, they wanted to avoid that, right? And initially, both of these types of pairs of sentences were given to BERT, and it makes predictions in the first round of its training. And the predictions would be just random. It will randomly say, yes, they are consecutive. Sometimes it says, yes, no, they are not consecutive. And half of them would be wrong because it was not, it's only the first step of the training. But then from the error that it produces, that error is used to calculate a gradient, and then with the so-called gradient descent, the gradient is backpropagated in the model to adjust its weights. So I'm not sure if I'm explaining too little or too much, but I will just continue anyways. Hopefully it benefits someone. So I would think of a neural network as a machine that has many knobs, right? When you use that machine for the very first time, all the knobs are at some random position, right? And you ask that machine for a prediction, and it will give you a very underwhelming prediction, something very stupid, very random, right? But then from that stupid prediction, you can calculate what we call a gradient. You calculate the error, you calculate the gradient, and interestingly, that gradient tells us the sensitivity of each of those knobs to the error. So the gradient tells us that if we go back and turn knob number 1 this much clockwise and turn knob number 2 that much counterclockwise and turn this and turn that to certain position and ask again, the answer would become slightly better. And we just do this repetition, which is called backpropagation, for training a neural network. We do this thousands of times. This is an iterative process. And then the machine, which is a universal function approximator, it will do what it is supposed to do. So that's how neural networks work. With the same idea here, we deal with a binary classification task. Initially, when we ask the question, it will give us some stupid answer. The answer itself doesn't matter in the first round, but the error from the answer tells us what needs to be changed in the weights of that model to give us good answers. Yes? We have labeled data because the labels come from the fact that we know whenever we took two sentences which were consecutive, algorithmically also we wrote consecutive next to it. So we have the labels, but in a smart algorithmic way, rather than some poor undergrad student trying to annotate them manually. Yeah. Question? Yes.
Maybe I missed it, but maybe introduction of the kind this is CLC
Yeah.
and CEP.
Yeah. CLC is the token that represents the beginning of a sample, the beginning of a sentence pair. Yeah. And then later, the embedding, the vector corresponding to it will be used for classification task. Just how we did it in Python earlier. And then SEP is just a separator. It just means the period at the end of a sentence. Instead of using period, they use SEP, and that's what it means. It just separates the two sentences. So it represents end of a sentence. Yeah. I mean, initially, it is just a character. It can be a special character. Later, that character becomes a vector. Yeah. Other questions? There's a question from the online participants. Please feel free to unmute and ask your question. You can also,
thank you.
Yes, we can hear you well.
Yeah, thank you. So I have a question is that we know that BERT models are encoder-only models, and then it is said that encoder-only model is not generative. But from this example, it seems that the encoder-only model like BERT, it can still do the next sentence prediction. So would you like to share your insights on this? Thank you.
Yes, the prediction, yes, thanks for the great question. The prediction is not predicting the next sentence out of nowhere. It is when BERT receives a pair of sentences, it can give us the binary classification of whether they were consecutive or not. This task of binary classification of consecutive and not classes is called next sentence prediction. Otherwise, this is not the next, this is not a text generation sort of idea. It's not generative at all.
So then the follow-up question then would be, in order to achieve this, does that mean that on top of the encoder-only model, you will have to actually attach some kind of classification layer on top of the original BERT encoder-only model to achieve this as well? Thank you.
Yes, yes, definitely. At the end, we need a so-called classification head. That can be as simple as a neural network layer that does binary classification. So something that takes all those neurons and compresses them into one unit, which would be a value between 0 and 1, right?
Great, thank you.
Of course. All right, so you can see that here for objective 1, this is the data, right? The data has, you know, this is segment A and segment B, and the label says is next, meaning that they were consecutive sentences in the original thing. And also you can see that there were some words that were masked. So maybe the original sentence was something like, the man went to the store, he bought a gallon of milk. Of course, for us, it's very easy to guess the missing words, but masking them essentially had two different reasons. One is that the model with masked words is going to develop the capability of guessing the missing word. And it was also used as objective number 2, which we're going to cover next. So for this sentence, the man went to the store, he bought a gallon of milk. We can see that they make sense next to each other, right? So the label is also is next. Here is another sample, which was used for pre-training. The man went to the store, penguin are flightless birds. So they don't make any sense. This is because also in the data that was used for pre-training BERT, one of them was taken from a Dostoevsky novel and one from Wikipedia page of penguins, right? And just patched together as one sample. Question? No question? Yeah? Yeah. I feel like with my example of Dostoevsky, I just ruined it. I think with the large number of training data, this is handled, because the most stark difference that we see between the man walked into the store and penguins are flightless birds is about the fact that they are from very different contexts rather than their styles. But you're right, we are risking that we might be also capturing the different literary styles of the authors. Yeah, but large amount of it was just stuff from the internet, which are just so mixed, right? Yeah, so the specific style of one, Russian author didn't have that much to do, couldn't really influence that.
But sequential sentences presumably wouldn't be the mixed styles, because recognized that they are mixed styles.
Yeah, mathematically speaking, yes, what you're saying definitely has happened, but it's about just the amount of impact that it could have done. It was so little that eventually the model works. Yeah, but mathematically speaking, yes, definitely all of that will be also incorporated. All right, so now objective number 2 was about masked language modeling, or so-called MLM. So with masked language modeling, you can see that the word that was masked in the original input is processed, right? And then eventually it is processed to a vector, and that vector corresponds to that vector has similarity to some standard embedding of words in the English language, right? So the input is I, mask word, a cat, and then mask becomes a vector in layer 1. Then it becomes another vector, and so on because of the weights, right? Eventually it becomes a vector, and that vector, in the very last layer, it was such that all the vectors become corresponding vectors for words in the English language, right? And then this vector represents the word saw, which is a good prediction in this context because it makes sense for a sentence, I saw a cat. I saw a cat, I pat a cat, I feed a cat, all of these make sense. So all of these will be good predictions, which will be rewarded in the, in the error function, in the loss function of that neural network. But if the prediction is I drive a cat, it will be a bad prediction, which is penalized in that cost function, right? So whenever the sentence, whenever it's not about context, so I didn't give a good example. Actually, it is based on what word was in the original sentence. So we knew what was the word in the original sentence. This was not just a guessing game of context, but rather, if the prediction is saw, the error will be 0, because in the original text, it was I saw a cat. But also, if the prediction is a vector that corresponds to the word see, as the vector for saw and see are very close to each other, that would be also somewhat a good prediction with some error, but good. But if the prediction is drive, as the vector for saw and drive are so different from each other, it will be penalized in the cost function. And then in the next step, the error from that penalty will be used to change some weights. And gradually it will learn just by large amounts of data. So now if we put these two objectives next to each other, this is what we have. So objective 1 and objective 2 were both used simultaneously. So next sentence prediction and predicting mask word, they happened at the same time. So that's the clever part of BERT, and I think what kind of distinguishes that project of Google to be one successful project among thousands of trials that people probably had, from the development of transformer architecture to the development of BERT, which was maybe a 1-year race between big companies to use transformers for a fundamental change in this field. So here is an example. My mask word is cute. He is very fluffy. This goes to BERT language model. I actually didn't explain the pre-processing part yet, but actually it's very simple. The pre-processing is made up of these 3 parts. The word my has a embedding in some basic, let's say, word-to-vec dictionary, right? That vector is here. We use that vector because we cannot do addition and multiplication with letters. We have to do with numbers, right? So for the word my, there is one specific vector in some basic dictionary, something like love, for those of you who are familiar with text mining. And then all of these words are in segment A, so a vector that represents segment A is added to them. And then this word is position 0, this is position 1, 2, 3, 4, 5. So correspondingly, here vector 0 is added here, vector 1 is added to the previous, to, you know, like for the word my is made up of 3 vectors, because it is not just my. What we are encoding in the pre-processing step is the word my, which is a vector. We make it a vector using a standard dictionary of, let's say, word to vec. And then we have segment A, and we have the position 1. These 3 together are added and they make this. So that would be a positionally encoded, segment encoded vector corresponding the word my. And that is just the input. Then that input, which already has segment and position encoded into it, goes through 8 layers of encoder. These are the 8 encoders. And then the final layer will be used for next sentence prediction here. All the other ones will be used for mass language modeling. Particularly those that correspond to masked words will be used for mass language modeling. You know, if fluffy goes up and eventually becomes a vector that is close to fluffy, that doesn't matter. But for the second objective, it is about what happens to this. What happens to this vector? This vector goes up and becomes this vector. So let's say that the original sentence was my cat is cute. If this is close to cat or dog, you know, or a word that whose vector embedding is close to cat, maybe kitten, that will be rewarded in the cost function. If it is Ferrari, it doesn't make sense for Ferrari to be fluffy, despite that it rhymes, right? So it will be penalized. All right. So I can see that some of you are already tired, but this is probably the last slide. So, or maybe just a few more slides. So pre-training loss. So let's say that this vector we get from the final model is this. That vector is attached to a softmax layer for classification. With 30,000 neurons, and this is because I think the dictionary they used at that time was a dictionary supporting 30,000 English words. So let's say this vector becomes a vector with, you know, these neurons, and then we compare using a cross entropy loss to the actual word that was missing, right? And based on that, we calculate the loss. So let me just give you an example. Let's say that the label we should have predicted was this 0, 0, 0. The label, the vector that we predicted is 1, 3, 7. The loss is, cross entropy loss is calculated like this. We have their difference is this, right? And we have softmax. Softmax is, softmax works like this. Softmax of y hat minus y is e to the power of 1, e to the power of 3, e to the power of 7 divided by this. So e is 2.7, right? E to the power of 1 would be 2.7. E to the power of 3 would be around 10. E to the power of 7 would be around 3 to the power of 7. So it would be a few thousand. So this will be 0.001, I guess something like this, right? And yeah, and the loss, right? Sorry. Yeah, I think then, yeah. The loss will be minus log of 0.98, which is a relatively small value. So it's, I think it's something like this. But just to give you the idea, right? This is, yeah, this is how the cross entropy loss works, right? A lot of fancy words, softmax, you know, neurons, one hot encoded, but actually when you look at the mathematics, it's very simple. All right, so that was pre-training. What about fine-tuning? So when the pre-training was done, essentially what we had was a foundational model, a model that can, quote unquote, understand language. And understand language by understanding the context and understanding the interdependence between words, not just something that converts words to vectors. Then fine-tuning was done for making a specific version of BERT for each application. So they used fine-tuning for preparing a version of BERT for single sentence classification, including sentiment classification. Sentiment. So if you have, you know, if you work for a bank and you have online reviews on I don't know, some online platforms about your bank, and there are like, I don't know, 100,000 of them, and you don't want to go over all of them and answer every single customer, you can just use a sentiment classification so that you can extract the negative ones and, you know, give, you know, diplomatic answers to the negative ones to show, you know, how good of a company you are by even handling, you know, criticism well, right? So this is one example, right? For that, you can use, you can load BERT and, you know, embed those words, those reviews into vectors, and then use the CLS vector to train a classifier, right? But also, you can use a version of BERT that is already fine-tuned for sentiment classification, if it is in the same language as the language of data you have. So for that, for the fine-tuning, they, they gave the input like this: I saw a cat, and the very first vector was used for comparing it to the class label. That's it. So thanks a lot for your attention. I think we still have like 10 minutes or so for more questions, but let's stay in touch. I'm available on Twitter here, also on LinkedIn. For me, I want to connect with all of you, but it's more difficult for me to find you. But if you're active on LinkedIn or Twitter, please find me and let's connect. And I'm happy to answer all your questions and also answer your questions during lunch. Thank you very much. Yes. Yeah, I think it's better with the microphone.
So thank you very much. So my question concerns that positional encoding, right? So
Yeah.
it was the only place that we cared about the order of the words, right?
Yeah.
And in there, actually, I mean, consider these two sentences. I want this, but not that, right? And then you can continue 100 pages after that, right? And the second sentence is like this. I want not this, but that, and then exactly continue the person. So the only difference between these two vectors are just replacing not from third to the second, and so
Replacing? I mean, in one sentence, you added the word not.
no, just replacing.
Oh, okay. Swapping. Okay.
Swapping, yeah. So,
Yeah.
So basically, the positions are all the same in a vector with length 10,000, let's say.
Yeah.
Right? Every position is the same, basically, except very, very slight part, right?
Yeah.
So these positions, so basically there are two vectors which are very close, and in the neural nets, basically the operations are all linear, except those non-linearity in the activation function.
Can I answer your question right now?
The question that I'm asking is that if, I mean, it's a little bit surprising that this is able to take care of this, because these two sentences that I mentioned are totally different, right?
I can answer you. So the thing is, like, for them, for people who develop BERT, they didn't train it on examples that always look like what you just said. So you managed to come up with a very kind of highly engineered example that is like a worst case thing that can happen, but the probability of that thing happening is very low when by the way that they were selecting, sentences for pre-training data. That doesn't happen at all. Even if it happens 1 out of million, so what? It's not going to impact the BERT model. Now the question is whether you should be concerned about something like that when you try to pre-train your own version of BERT. And the answer is you should only care as much as that coincidence is likely, which I would say is very unlikely. One sample doesn't impact the result of a neural network.
Yeah, but what I'm saying is that at least in the case of graphs, right? When you have a graph, the context of positional encoding in graphs usually incorporate with the eigenvalues, right?
Yeah, but here, I mean, as everything is based on large amounts of data, we don't need to worry about these like specific examples.
No, it's more or less the same in the graph context, right? But what I'm saying is that the positional encoding, instead of just looking to these simple numbers, 1, 2, 3, 4, we can just incorporate more complex, more informative.
Oh yes, right? I mean, to be honest, it is a bit more complex. The version I described was a kind of a simplified version of it. It's not really attaching numbers 1, 2, 3, 4. It's like adding 4 waves. Yeah.
Because it's very likely to be undermined on this node, right?
They use something that is more versatile and more variable than just numbers 1, 2, 3, 4. Yeah. Other questions? There's a question there. If you can get the.
So like for the BERT, without the positional encoding, like it would be somewhat like positional invariant for like where the token is. Would you say?
Sorry, positional?
Invariant. So like doesn't matter where you put like Bob dumps Alice or Bob Alice. It's processed the same way without the positional encoding because of just the nature of neural network.
So the positional encoding was like an additional thing that they included to incorporate the context and sequence of the words.
So it gives a little bit of uniqueness for like where the word is based on the position. How much of like noise should you inject? Like normally on BERT, like you use sine or cosine.
Pretty much everything you saw was rather automatic. They didn't need to decide on how much noise to inject. There were some rather arbitrary choices which they made by trial and error. For example, here, for example, the fact that they did 50-50 here, this was somewhat empirically decided, right? Or the fact that 15% of the words were masked was another rather arbitrary choice that they had to kind of come up with a number for it empirically by trial and error. So they learned that 10% is too little, 20% is too much. There are undesirable effects to the both extremes, and 15% was the sweet spot. So in the development of BERT, there are like a few of these, like 5, 6 things that they had to decide by trial and error. Other than that, everything else was automatic. There's a question here, if you don't mind.
So I know we're in the hand close to lunch, but maybe this is a discussion we can have there. But in one of your early slides, I think part 1, you showed the progression of language modeling. After BERT, we have T5, GPT-3, Llama 2, and Gemma. I'm wondering, have these newer models, represented some form of a revolutionary development that we have not discussed?
So yeah, BERT, T5, and GPT-3, they were all rather similar in terms of what they could do, and yeah, the rough performance measures they had. Then Llama 2 is after the success of ChatGPT, so it is something fundamentally different. And Gemma, how it compares to Llama 2, it depends whether you ask Google blogs or you ask Meta blogs. So Google has like a table that shows Gemma just outperforms Llama 2 on everything by large margins, but that's debatable. So, but my understanding is that Gemma and Llama 2 are currently the best open models that we have access to. And Gemma is just from February or March 2024, so it's relatively new. And then BERT, T5, and GPT-3, GPT-3, I believe. They are from the previous generation. Yeah, and are somewhat similar. So yes, reinforcement learning with human feedback, which was used in ChatGPT, was very fundamental in allowing these models to make new computations and predictions possible. Yes, so I think that was the revolutionary thing. And yeah, that's something that it seems OpenAI did it earlier than others. But now all the models, or this like recent generation of models, all of them have reinforcement learning with human feedback somewhere in their development. Yeah. Other questions? All right, so the Python code that I showed you, it works, but there's an important part that was missing from the screenshots on the slides. The important part is that the very recent version of TensorFlow text has an issue with some other libraries. So I have this Python code, and I will put it on my own personal website. So if you go to my website in 24 hours from now and search Fields Institute, there will be a link to download the slides, and there will be a link to download this code. All right, so just to make sure that it works, here, this is just a fresh, Google Colab session. And I think already Google Colab has TensorFlow text, but I'm loading a very specific version of it, which is from 6 months ago, because the very recent version like throws an error or something, at least for this code. I'm importing these. These are the two parts of the function, right? This is the function I showed you also. This is the function I showed you, right? And this is the example. So we have two different sentences, right? The first sentence is kind of spammy. The second one is just an innocent email. You can see that loading it takes a bit of time. And then we can use that function on these input, just to give you the idea of whether the vectors are somewhat similar or not. So I have 6 input here: banana, grapes, mango, Jeff Bezos, Elon Musk, Bill Gates, right? So let's use BERT to embed these. Essentially, I'm taking this as a sentence, right? So banana is a sentence here, right? All right, so now they are embedded. The similarity between the vector representing banana and the vector representing grape, the similarity is 0.99. This is what we mean by BERT understanding quote-unquote language. It embeds banana and grape closer to each other in the vector space of that higher dimensional space. Now, if we want to do a binary classification that classifies fruits from everything else, it can do it, right? And what about similarity between banana and Jeff Bezos? Let's try that. This is the similarity, 0.84. So they are not totally dissimilar, but less similar than grape and banana. And similarity between Jeff Bezos and Elon Musk, 0.98. Why are they similar? Because in the text that was used for developing BERT, both of them were mentioned in, I don't know, tech articles, in articles about rich people, in articles about US, right? So that's the similarity. It is about their co-occurrence, essentially. The fact that both of them are CEOs and so on, right? So that's it. Now, what this means, also instead of these, of course, we can have sentences, right? Just like these, right? And look at the similarity between them. But yeah. So for that, you just need to replace, you know, anything you want, you can put in the code and see how it works. All right, so if you go to my website, just Google my name, Samin Aref. In 24 hours from now, there will be something that says Fields Institute with a couple of links. Hopefully one link for part 1 of the slide, one link for part 2, and one link for this Python, short Python code. Any other questions? Yes. Let's get the microphone so that everyone, yeah. I got it. Thank you. Go.
About the sentence example that you show in the code, you have 2 sentences, yeah, and many vectors as a result.
No. Here I'm just in my function. I'm only extracting the CLS output token, not many vectors. So
in that one,
this
yes,
part here, this part means give me only the pooled output. Pooled output is the vector corresponding to the CLS token.
Ah, okay.
To the very first token from that output table, if you remember.
Yeah. Could you show us the similarity between the
these two we can try that. So
vectors are between -1 and 1, or not necessarily?
Let's see. So we have A0, right? This is A0, it's a 7, right? This vector and A1, right? So I just use cosine similarity. Probably, I mean, they should not be similar. Let's see. A0 and A1, right? You can see that there are some similarities, right?
But
I mean, but whether this works or not is about also your label data, right?
Yeah, it depends of the source of the data set itself, because it's learning from some place.
No. BERT just BERT embeds these two such that their CLS tokens have a relatively high cosine similarity. But this is, I mean, there are many reasons to this. It could be the case that, you know, maybe the BERT we have loaded, what is it? On case. Yeah, this is, I guess this is English only. Yeah, anyways, these two are similar, but ideally they are sufficiently distant from each other to the point that we can indeed train a spam detector by this.
Okay.
Yeah, this was a coincidence.
Yeah, it's okay. But vectors are between -1 and 1 when we see the
each
the
coordinate
98.
of the vectors.
Yeah.
Yes, they are between -1 and 1, each coordinate.
Okay.
Yeah.
Thank you very much.
No worries. Other questions? All right, thank you very much for your attention, and I'm happy to chat more during the lunch. Thank you.